Hi there. Previously, we learned how to solve basic logarithmic equations. In this lesson video, we will learn how to solve the more complex equations. Solving complex logarithmic equations will require what we call as laws of logarithms. Hence, the objectives of this presentation are: we apply the laws of logarithms to simplify logarithmic expressions, and we will also apply these same laws of logarithms to solve logarithmic equations. Let us start with what we call as the common and natural logarithm. Logarithm with base 10 are called common logarithms, while the base e logarithms are called natural logarithms. So as we can see from the illustration, a log base 10x can be written as log x or lgx, meaning to say, if the base is 10, there is no reason for us to write the base 10. Or in reverse, if written log x, we should know that the base is 10. Unlike the other bases, you have to write the base of the logarithm. In the case of log base e, whenever the base is e, we can rewrite the logarithm as ln x. So an ln x means log base e of x. So for example, log 1000 equals 3 means there is a base 10 here that we cannot see, but we should know that the base is 10. So when we rewrite this in exponential form or in exponential equation, as we learn, this is base 10 raised to 3 is equal to 1000. On the other hand, if we have ln x, we know that this is log base e of x is equal to 5. Therefore, this is the same as e to the 5 is equal to x. Before we solve the more complex logarithmic equations, let's have a quick review on how we solve basic log equations. The solution to this equation is that we need to transform this equation into exponential form. And we learn that to transform this to exponential form, we get the base 4, we raise it to the exponent 2 because the log is the exponent, and this will be equal to x plus 3. As we can see from my solution here, 4 squared is equal to x plus 3. Then simplify accordingly. 4 squared is equal to 16. So that 16 equals x plus 3. Solving for x, this is 16 minus 3. So you have 16 minus 3. And 16 minus 3 is equal to 13. So the x is equal to 13. Now for logarithmic equations, we said we have to watch out for some restrictions. We learned that this expression, whatever expression is written here, it must be greater than 0. So that is what we did. X plus 3 is greater than 0. This means x is greater than negative 3. So this is a restriction. So how do we use this restriction? Every x that we get from the solution should satisfy the inequality. For example, 13. 13 is greater than negative 3, which is the restriction. Therefore, we can accept the solution to be x equals 13. So we go now, what if we have log base 2 x minus 1 plus log base 2 x minus 4 equals log base 2 of 2x minus 6. So this is something that we have not solved before. So how are we going to use whatever we know, or is there something that we need to know more in order for us to solve this equation? This is where the laws of logarithms will come in. I'll introduce the 3 laws of logarithms. First, we have to note that if a and x are positive numbers, and a is not equal to 1, then we can have all these laws of logarithms be applied in solving equations. Let's start with the first one, the power law. The power law states that if you have an expression x to the r, and this is under the log base a, note that we can rewrite this logarithm in such a way that we put the exponent before the logarithm, and it becomes r times log base ax, meaning to say they are the same. The product law. In the product law, you have a log base a, and the expression is a product of two expressions. In logarithms, we can actually split the two, and we write log base a of the first expression plus log base a of the second expression. Note that the pattern will be the same for the quotient. That is why we call it the quotient law, because we have a quotient. For the quotient, so provided you have log a x over y, you can split the logarithm into two, log a of the numerator x, as we can see, minus log base a of the denominator y. Note, however, that log a xy, you have to note this, log a of x over y is not the same. Do not make the mistake of saying that it's the same with this, because they're not. Okay? So when we see log a x over y, it should be the difference of log ax and the log ay. Let's start first by using the power law in simplifying expressions. Please look at my solutions while I'm discussing. For log base 2 of 2 square root of 2, the idea is we rewrite square root of 2 as we know that is 2 to the 1 half. So that means log base 2 of 2 to the 1 times 2 to the 1 half. Log base 2, so if you have the same base, you can actually combine the two expressions 2 to the 1 and 2 to the 1 half. And when we combine them as a product, we copy the base 2 and then we add the exponents. So 1 plus 1 half is equal to 3 over 2. Now, this is already like log base a of x to the r. That means the r can be written before the log. So the 3 over 2 went down, so we can say went down before the log, as we can see here, and you have log base 2 of 2 left. So this is 3 over 2 times log base 2 of 2. And from the special logarithms, we know or we learn that log base a of a, when they're the same, the value is just 1. So 3 over 2 times log base 2 of 2 is the same as 3 over 2 times 1, or equal to 3 over 2. So this is the simplest form of log base 2 of 2 times square root of 2. In another example, we have the quotient of log a8 and log a4. Take note, this is not the quotient law. Remember what I've said? The quotient law should have the form x over y and not log over log. But to simplify this using the power law, we know that 8 and 4 can be written as base 2. So 8 is 2 raised to 3 and 4 is 2 squared. Now, with the presence of the exponents, we can now transfer these exponents before the log. So 3 goes down, 2 goes down, and then you have 3 log a2 over 2 log a2. Since these two are the same, we can cancel them, so the numerator and the denominator, so we are left with 3 over 2. So as we can see, this is also equal to 3 over 2. Okay? Then let's look at the product law. So for the product law, again, we review the rule. It says log a of xy is equal to log ax plus log ay. So in the product law, it could be that you're given this and you expand it, or you're given this and then you compress the expression. So in this example, we are given the expanded form and we have the sum of two logarithms. And also take note that when you expand the logarithm, the product xy, you have to have the same base. So we have to check that first, log base 6 and log base 6, meaning to say the product law can be applied. So when you compress that into a single log, you have the log base of the same base 6, and then you have the product now of 3 and 2. So you have 3 times 2. 3 times 2 is 6, so the log becomes log base 6, 6, which is another application of log base A, which is equal to 1. Therefore, the answer is equal to 1. In the second example, we have 3 logs, so we can extend the product law even to more than 2 expressions as long as they have the sum and then you have the same base. You can even take it one by one. For example, you can combine the first two and then connect the third one. But if all the logarithms are with plus sign, we can just do that in one step. So log base 2 of 40 plus log base 2 of 0.1 plus log base 2 of 0.25 is the same as the single log base 2 with 40 times 0.1 times 0.25. If you simplify the product of 40, 0.1, and 0.25, that becomes a 1. And this is an example of log base b or log base a of of a number 1, and that will be equal to 0. That is why the answer to this, or the simplest form of log base 2 of 40 plus log base 2 of zero point 0.1 plus log base 2 of 0.25 is equal to 0. Okay, so that's how we apply the product law. Then we have the quotient law. This time we started with the expanded form, and how do we know that it should be under quotient law? Your q is the minus sign. They have the same base, so we can combine or we can compress the logarithm into a quotient of 8 and 2. So log base 4 of 8 minus log base 4 of 2. So remember, we have log base a of x over y is equal to log base a of x minus log base a of y. So from here, if we started with the expanded form, we can rewrite it in this manner. So you have log base 4 of 8 over 2, and 8 over 2, as we know, is 4. And this is another example of log base a of a or b of b. As long as they have the same value, the answer is equal to 1. In the next example, we can see you have a log base 2 of x to the 4 minus sign, so minus log base 2 of x raised to 3. So it's another application of the quotient law, and if we apply it, we compress it into a single log, same base, base 2, and then we have the quotient of x to the 4 and the expression x raised to 3. Simplifying log base 2x to the 4 over x cubed, that's 4 and 3. So take away 3 of the x. So you have a single x left for the x to the 4. And unlike the other examples, as we might hope that it will be a number, there is nothing that we can do anymore with the log base 2x. So we can stop at log base 2x. So in general, when we have logarithms with the same base, and you see an expression like log base am and log base an, we can solve equations like this by just relating the m and the n. So m is equal to n. So this is done whenever, so take note, this can only be done if you have log base a and log base a. If the bases are not the same, then we cannot equate m and n. So this is the idea that we use when we solve logarithmic equations with the same base. Let's look at my first example. In this example, I have log base 2 of x minus 1 plus log base 2 of x minus 4 equals log base 2 of 2x minus 6. So together with the idea of the one presented earlier, log base a of m is equal to log base a of n, we said that this will be m equals n. But this will only make sense if you have a single log on the left and a single log on the right. So as we can see in the example, this is not yet the case. However, we already learned how to compress logarithms. Since these two logarithms are sum of two logarithms, then we can apply the product law. So from the plus sign, we compress the logarithm into a single log, but we have to express x minus 1 and x minus 4 as a product. So with this, we have log base 2 of x minus 1 times x minus 4 equal to the other side log base 2 of 2x minus 6. From here, we can already see that there's a single log on the left and a single log on the right, and they have the same base. So this is where we can already apply this idea. So since they have the same base and we're working with one log on one side and one log on the other side, we can immediately equate x minus 1 times x minus 4 to 2x minus 6. And the logarithmic equation is now changed into a quadratic equation. Quadratic equation because when we expand x minus 1 and x minus 4, we get x squared minus 5x plus 4 equals to x minus 6. So from here, work on your algebra until you get x squared minus 7x plus 10. You factor it the way we solve quadratic equations, and it will give you x minus 5 times x minus 2. And we know that if we have the factors, we split the factors and equate them to 0. So x minus 5 is 0, and x minus 2 is equal to 0. So x is equal to 5 from the first, and x equals 2 from the second. Again, unlike the exponential equations, the logarithmic equations have some restrictions. And we check, well, the base is okay, it's base 2. There's nothing that we can, there is no restriction for the base 2. But for the expression x minus 1, x minus 4, and 2x minus 6, we know that each of these expressions should be greater than 0. So that is what I did in my solution. So we have x minus 1 should be greater than 0, x minus 4 should be greater than 0, and 2x minus 6 should be greater than 0. Simplifying this inequality, first restriction is that x must be bigger than 1, x must be bigger than 4, and x must be bigger than 3. Okay, but if we will combine all these restrictions, the biggest restriction is that x must be greater than 4. In the first, it says 1, bigger than 1 is okay. But when we go on the 3, it says bigger than 3. But for the 4, it says it should be bigger than 4. So it should matter for all. So we should consider x greater than 4 as the main restriction. So in the computation that we have, in the solution that we have x is equal to 5 and x is equal to 2. So we have to check this with our restriction. You can even do it one by one. 2 is greater than 1, but 2 is less than 4, so it will fail. 2 is even less than 3, so 2 will fail. If you have 5, 5 is greater than 1, 5 is greater than 4, 5 is greater than 3. Therefore, x equals 5 is the only solution to this logarithmic equation. But what can we say about x equals 2? It is not a real solution, but what we call as the extraneous solution. Note, extraneous solutions should not be included as the final solution, but we call them as extraneous because they seem to be solutions even if they will not pass the conditions given by the restrictions of the expression in the logarithmic equation. Here is another example. log base 3 of 2 plus log base 3 of x plus 4 is equal to 2 log base 3x. And we will see how is this different to the one we just solved. Or in some ways, how is it similar to the one that we previously solved? So again, let us be guided by the idea that if we have log base a of m equals log base a of n, then that means m is equal to n. But this can be applied only if we have a single log for each side. So that means we have to fix the log base 3 of 2 and log base 3 of x plus 4. Again, it's a plus sign, so we can compress that as a single log, but we have to express the 2 and the x plus 4 as a product. For now, let's copy 2 log base 3x. Now, for log am equals log an to work, note that there are no numbers before the log, but there is a 2 before this log base 3x. But there is a way to rewrite 2 log base 3x, and that is by the use of the power law. So it's the reverse of the power law. This 2 can be written as the exponent of x. So we can rewrite that as log base 3 of x squared. So from here, we can already see log base 3, log base 3. This is like our log am, log an. So we can now equate the 2 times x plus 4 to that of x squared. And then you will obtain again a quadratic equation that you need to solve. You do the factoring and then equate each factor to 0. So I need you to review your factoring during your free time. So solving for x is 4 and x is equal to negative 2. And just like any logarithmic equation, we have to check for restrictions. How do we check? We go back to the expressions x plus 4 and the x, those that involve x. So first, x plus 4 must be greater than 0. X must be greater than 0. X plus 4 means x greater than negative 4. And then we check. What did we get? Let's start with 4. 4 is definitely greater than negative 4. And 4 is greater than 0, so x equals 4 will pass the conditions. In the case of x equals negative 2, yes, it's greater than negative 4, it's higher than negative 4, but negative 2 is not greater than 0 because it's a negative number. So again, we have the real solution to be x equals 4, and it's the only solution, while x equals negative 2 is not a solution but only an extraneous solution. Here is one more example. 2 log base p of 8 minus log p4 is equal to 2. Again, the idea is we have to express the logarithms into a single log. Now, as you can see, this might be already slightly different to the one we have been solving because it doesn't seem like a log base a of m equals log base a of n because primarily 2 has no log before it. Okay, but we can work on this and let's find a way. Maybe we could apply one of the laws of logarithm or the laws of logarithms, the combination of them. Okay, now there's a minus sign which is giving us an idea that there is a possibility that we can combine this by using the quotient law. Note, however, that there is the presence of this number 2. In the quotient law for logarithms x over y, it is very clear that we can split the 2 or from the subtraction we can compress it into a single log only if there is no other number here aside from 1 because that's 1 times log ax and 1 log ay, or we can think of that as like a coefficient, but that is not the case for the 2. There's a 2 log base p of 8, but there is a way to rewrite this so that the 2 will not be written before the log, and that is by the use of the power law. So in the power law we can Put back the 2 as the exponent of 8, so it becomes log base p of 8 squared minus log base p of 4 equals 2. Then we have now log base p of 8 squared over 4, and 8 squared, as we know, is 64, so that's 64 over 4 equals 2, or log base p of 64 over 4 is equal to 2. Simplifying that, we have log base p of 16 is equal to 2, and instead of applying this is a basic logarithmic equation which just require the conversion from log to exponential form, and that is p squared is equal to 16. Remember the basic equations for log? P squared is equal to 16. So in your case, you have to be aware as well, when do we use this idea and when is it that we solve the logarithmic equation when it's a basic form. Okay, so when it's a basic form, we apply the conversion to exponential, which will be again p squared equals 16. P squared is equal to 16 means P is positive and negative. Do not forget the positive and negative square root of 16. So there are two possible values, the plus and minus 4. And then with that, we have to check the conditions. The only variable here is the P, the base. So we know from the conditions of logarithm that base are greater than 0 and base cannot be 1. So we apply that to p because the base here is p. P must be greater than 0 and p cannot be equal to 1. But in the case of our solutions, 1 is positive and 1 is negative. So the negative 4 will not pass the condition because it's a negative number, while 4 is greater than 0 and it's not equal to 1. Therefore, the only solution is p equals 4. Okay, so here we will revisit the graphs and we'll see how the knowledge of the laws of logarithms and solving logarithmic equations can help us find the x-intercept and the y-intercept. So in our other lessons, we only learn how to graph by translating the axis of the given basic function or parent function. But for now, let's apply the concept of solving equations in finding the intercept, the x and y intercept of this function. So same with any function or equation, when we look for the x-intercept, we always set y to be 0. And this is our y. So make that 0 is equal to 4 log base 2 of x plus 1 minus 8. And then manipulate this so that you can isolate the log and you can have a number on the other side. So minus 8 goes to the other side, becomes positive 8, and you have 4 log base 2 of x plus 1. There is this 4 that we do not need, but instead of using the power law, you should be able to recognize that 8 and 4 are two numbers that are related. So we can just divide both sides by 4. So we have 8 over 4 is equal to log base 2 of x plus 1. So you have 8 over 4, 8 over 4 is 2, equals log base 2 of x plus 1. So it's a basic equation that can be solved by transforming it into an exponential form. And how do we transform? Get the base, that is our base, raise it to the exponent 2, and then go back equals to x plus 1. 2 squared is 4 equals x plus 1. 4 minus 1 is 3, so x is equal to 3. And then check a restriction, x plus 1. Note that x plus 1 should be greater than 0, and x is greater than negative 1. So we have x equals 3 is an acceptable solution. Therefore, our x-intercept, if we will be graphing this function, we will have x equals 3 as its x-intercept. Finally, we solve for the y-intercept, And the same idea, if we look for the y-intercept, we set x is equal to 0. Setting x equal to 0 means we have to substitute 0 to x in the expression. So we have y is equal to 4 log base 2 of 0 plus 1 minus 8. Simplify this, we have y is equal to 4 log base 2 of 0 plus 1 is 1. And as we know from the special logarithms, log base 2 of 1 is 0. So 4 times 0 is equal to 0. So we have 0 minus 8, which is negative 8. So the y-intercept is equal to negative 8. Now note there is no restriction for this y-intercept. We're not talking about the x, so there's no restriction for the y. And if we will be graphing the function, we can expect that the y-intercept will be at negative 8. So in the graph, so just to give you an overview, we will be having an x equals 3 as the intercept, and we will have negative 8 as the y-intercept. Okay. Now knowing the translation of axis, this x plus 1 will move the y-axis. Well, we translate the axis to x equals negative 1, and we have the minus 8. That means it's down. The horizontal axis will be down by 8 units, and it will be exactly at the same point that we were considering as the y-intercept. Okay, so to graph, we have to cross this point. It's a positive 4, so it must be an increasing, although we cannot see it from the whole graphing paper. So it will go down like this, and it will be asymptotic with x equals negative 1. Okay, but this is how we can see our x-intercept and the y-intercept. Okay, so here is the better copy of the graph. So we have x equals 3 as the x-intercept and y equals negative 8 as the y-intercept. Okay, so that's how we apply the idea of solving equations, logarithmic equations, in finding the intercepts. For you to think about, so what if I have the function 2 log base 3 of x minus 1 plus 5? Why is it that this function, when we graph, there is no y-intercept? Okay, so I'll be leaving that problem with you, and probably you can try graphing it or solve for the y-intercept so that you will see why it will not have the y-intercept. Okay, so that's for this lesson video. So we learn how to, or first we learn the laws of logarithms. We also have a preview or a quick idea on common logarithms and natural logarithms. And then we studied the laws of logarithms, and we applied them to simplify logarithmic expressions, and we also applied them in solving logarithmic equations. So I hope that you were able to learn something from this video, and if you need to review the ideas, you can simply rewatch the video. Okay, so that's all for this lesson. Thank you.